So this question is about half-life. So we've got an activity curve, and you can see some of the points are not quite on that exponential that we expect. And the logic behind that is that rate of decay is a random process, so you're not always going to have the exact number of decays you expect, especially for a small number of radioactive atoms in your sample. Right? The more you have, the closer you get to being the average all the time. But that leads to random deviation from the expected decay. And the question then goes on to ask to estimate the half-life. So to do this, we have to go back to the curve. We started about 240 becquerels of activity. After one half-life, that will have halved down to 120, which you can see happens after 1.2 days. So our half-life is 1.2 days. Right, there's not a lot of work into right there. You could maybe write a C graph, or you could say activity at 0 and activity at 1.2 days is 240, 120, therefore half of 1.2 days. Beautiful ways to it. So gamma rays is metastable technetium, right? The nucleus decays from an excited state to a stable state without actually having any real change, but gives out the energy that it had. Is a gamma ray, which is a very high energy electromagnetic radiation photon. Right, it's released in nuclear reactions, carries a lot of energy, doesn't carry any mass or charge. Right, so if we have this solution of technetium, it goes from 856 counts down to 53 counts in 24 hours. So we can just sort of go, well, how many halvings has it undergone? How much has its activity decreased by? And it's decreased by a factor of 2 to the 4, so it's halved 4 times. We've had 4 half-lives in these 24 hours. That tells us that a half-life is 6 hours. Whereas if we put A on A naught, we get 1 on 2 to the 4, which tells us that the N is 4. Just fixing up a mistake. Right, the second part goes, well, what would the activity become after 4 more hours? Right, so that's 28 hours. 28 hours is 4 2/3 half-lives. So we use our half-life activity equation. The activity, it's the original activity, the 856, times a half to the power of 4.67. Or we could have done 53 times a half to the power of 0.67. That would get us the same answer, because we take what we have at the end of 24 hours and we go, well, let's go another 2/3 of a half-life along. Right, but that's not how I've chosen to proceed here. Taking the numbers, putting it all in, we end up with an activity of 33.7 becquerels. Now, the question asks, why is using the technetium superior to using a very long half-life? So short half-life has several, and it clears the system much more rapidly, right? You don't have radiation still in people's bodies 10 years later, right? And because the activity is relatively high for a given dose, you can get a strong signal as the radioactive signal decays, right? Whereas the 10-year half-life, with that relatively low amounts of radiation, the signal is much harder to release, so we get more accuracy with the 4-hour half-life, 6-hour half-life, sorry, than a much longer half-life. One last point, you would need a much larger dose of the long half-life material to get the same activity, right, which may well have health effects. The final part of this problem is compare the 6-hour half-life to a much shorter 10-second half-life. So a 10-second half-life isotope would have decayed away to almost nothing before the experiment really begun. Right, it would be almost invisible within a few minutes. Right, so useless for most diagnostic tools.